Okay, I guess we can start for today now. So it's my great pleasure to welcome Professor Gabor Lugosi to speak at this event. He's highly regarded researcher and a great speaker. We were very keen to have him visit us in 2019 for our first event on program on advances in applied probability. That didn't quite work out for logistic reasons, but we're very happy to have him this time, and we hope to have him in India soon when things normalize. I'll just speak very briefly about his background. So Professor Lugosi is an ICREA research professor at Pompeu Fabra University in Barcelona. His interests include the theory of machine learning, combinatorial statistics, probabilistic inequalities, random graphs, and random structures and information theory. His PhD is from Hungarian Academy of Sciences, from Science. He's on the editorial board of many prestigious journals, including Mathematical Statistics and Learning, Annals of Applied Probability, Probability Theory and Related Fields, Journal of Machine Learning and Research. And he's written many books which have become popular in the learning and probability community. Uh, Foremost being Prediction, Learning, and Games. One way for me to measure popularity of a book is how often I lose it to the students. So this particular book, I've lost it twice already. It just doesn't come back. Concentration inequalities, a non-asymptotic theory of independence, combinatorial methods, intensity estimation, a probabilistic theory of pattern recognition. So many of you, I'm sure, have seen some of these books. They're all excellent. So Professor Lugosi, we look forward to your talk. You'll be speaking today on root finding and broadcasting in random recursive trees. The screen is yours.
Thanks so much, Sandeep, for the nice introduction. I really hope that we can do this in person next time. But until then, well, we're doing what we can. So let me try to share my screen. Let's see. Here it is. Yeah, can you see this? I'm going to talk about root finding and broadcasting in random recursive trees. I will explain what this is. So this talk is based on two papers, one with Sebastian Vivek, who is at Microsoft Research, and Luc Devroy, he's at McGill University. And the second one with Luigi Dario-Berri, he's also at McGill, Luc Devroy, and Vasily Kivalona, she's a PhD student finishing and looking for a postdoc position. So if you're interested in excellent postdoc, let me know. All right. So so what is this problem about? So the first problem, well, both problems can be cast in a big family of problems that may be called network archaeology. So what's network archaeology? These are dynamically growing networks, and we've seen many of these in social networks or epidemiology. I don't have to talk too much about the importance of that. Rumor spreading computer networks. So when a network grows in time, and we observe this network when it's already very large, and we would like to know something about the past of this network. So we only observe a present-day snapshot of this network, and we would like to say something about the past. So these questions include: who is patient zero in an epidemiological context? Who started a rumor? The nodes in this network who are influential today have they always been influential, and so on and so on. Okay, so these are the type of questions that belong to this area of network archaeology. When observing a large networks that we know that has been growing, we would like to say things about what happened in the past. Okay. So in this talk, I'm only going to talk about very simple networks that are actually trees, and but often these networks are modeled as by very simple random growth dynamics. So here vertices arrive, let's say, one by one, and when a new vertex arrives to the network, then it chooses, according to some very simple rule, it chooses some vertex or vertices to attach to. Okay, so the simplest model is called the uniform attachment model. When the new vertex that arrives attaches to a randomly chosen vertex. Okay, so among all vertices that are already there, it chooses one uniformly at random and attaches to it. This is the uniform attachment model. And when the vertex only chooses one vertex to attach to, and we start with a single vertex, then this is going to be a tree. Okay, this is called the uniform random recursive tree that is grown like this. Okay, but often there can be other types of attachment rules. For example, in the famous preferential attachment model, when a vertex arrives, then it's more likely to attach to a vertex that already has many connections. Okay, so the probability of attaching, so the attachment is still random, but the probability of attaching is influenced by the degree of the vertices that are already in the network. Okay, so in the simplest preferential attachment model, that's called the linear preferential attachment model, the probability of attaching to a vertex is proportional to the degree of that vertex. Okay, so in this talk, these are the two models that I will consider: the uniform attachment and the preferential attachment models. And in the simplest case, when these are trees, okay, so when a new vertex arrives, it attaches to just one vertex. All right. So these are called as I already said, the uniform random recursive tree when the attachment is uniform. The preferential attachment model in the simplest linear case is when the probability of attaching is exactly proportional to the degree. This is a tree that actually has been around for a long time, and it's called a plane-oriented random recursive tree. For reasons I'm not going to explain, but there's a very simple way of a different way of describing these trees. Okay, and these have been, such trees have been very well understood in probability. Okay, so the first problem that I'm going to address is what we call the finding Adam problem. Okay, so so what we are shown is a large tree without the labels. Okay, so we know that vertex 1 arrives at time 1, vertex 2 attaches to vertex 1, then vertex 3 chooses a random vertex, attaches to it, and so on. So this tree grows like this, but now we erase the label. So all we observe is the combinatorial tree. Okay, but we would like to know, and this tree is very large, so imagine n to be huge. But what we would like to do is to find the root of the tree. So the root of the tree is vertex number 1. That's Adam. Okay. So the question is this possible? In what sense is it possible? Okay. So if I show you a huge tree that has been grown according to these uniform or preferential attachment models, can we identify vertex number 1? Well, yes and well, no. The immediate answer is no, since vertex 1 and vertex 2, they are the same, right? They are completely equivalent, because at time 2, when vertex 2 arrives, then the tree is just these two vertices connected by an edge, and from that moment on, these two vertices are indistinguishable. Okay, so so in order to make this problem a little bit more meaningful, but we are allowed to select, when we want to identify the root, we are allowed to select not just one vertex, but a set of vertices. Okay, so we are allowed to select, let's say, k vertices. And what we would like to guarantee is that the root is in this set with high probability. Okay, with probability at least 99%. Okay, more generally, we are given a probability of error that we allow, that's epsilon, and now we are allowed to choose k vertices in any way from this tree, and we would like to guarantee that the root is among those k vertices with high probability. Okay, so the question is, how large does this k have to be? Okay, so clearly this depends on the probability of error and on the size of the tree. Okay, so large trees are expected to be more difficult, right? It's more difficult to find the root in a large tree, and if epsilon is very small, then the problem is also more difficult. So the question is, how large this k have to be such that we can guarantee that the root is in a set of k vertices that we can choose. Okay. Please interrupt me if anything is unclear. All right. So here's these are images that I chose that I stole from Igor Korchemsky. So this is what a uniform attachment tree looks like with 5,000 vertices. So this is what we are shown, and we would well, of course, this tree is drawn according to some kind of optimization algorithm that you see. Not all edges have the same length, so these are optimized for viewing pleasure. So maybe this is the root here in the middle, but who knows? We don't know that. So this maybe here is the root. Maybe this is the root. Okay. So the question is, how many vertices do I have to pick from this tree such that with high probability I can guarantee that vertex number 1 is among them? This is the same tree with 10,000 vertices, with 15,000 vertices, 50,000 vertices. So you see when the tree is big. So now where's the root? Finding Adam is now doesn't look that easy visually. Okay, all right. Preferential attachment trees look very different. Actually, this is known that they have much bigger hubs. So there are vertices that have much larger degrees. The maximum degree in a uniform attachment tree is about the logarithm of n. And here, a maximum degree is about square root of n. So there are huge hubs in the preferential attachment trees. So the problem looks kind of different. Okay, so I will talk about this. So let me summarize the results of this. So maybe surprisingly, the minimum number of vertices that I have to choose in order to guarantee that the root is among those k vertices with probability at least 1 minus epsilon doesn't depend on n. Okay, so finding the root in this tree, in this gigantic tree with 50,000 vertices, is not much harder. It's not harder. Well, it is a little bit harder, but not essentially harder than finding the root in a small tree like this. Okay, so it doesn't matter. And if you have 1 million nodes or 100 million nodes, the problem doesn't get harder. Okay, so that's one of the surprises, and this is true for in both models. So that means that that the k only depends on epsilon. And the second kind of surprise that was surprising to us is that finding the root in a preferential attachment tree is actually harder than in a uniform attachment tree, even though you would expect maybe that that in a preferential attachment tree, since there are these big hubs, the root should be a big hub like that, but it is not the case. It is provably easier to find the root in a uniform attachment tree, and by easier, what I mean is that this k of epsilon is smaller. Okay, as a function of epsilon, it's a smaller function than in the case of preferential attachment tree. Okay, so let's see how one can go about this kind of problem. So how do we find the root of such a gigantic tree? Well, the first idea that comes to mind is that old vertices are likely to have higher degree, right? Because they arrived at the beginning of time, so they had more time to grow. Okay, for example, in a uniform attachment tree, it's very easy to compute what the expected degree of the root is, right? Because at time 2, when the second vertex arrives, then the root has degree 1 with probability 1. And when the next vertex arrives, then it attaches to vertex number 1 with probability 1/2, at time 3 with probability 1/3, at time n with probability 1 over n, right? So at time n, it's the harmonic number, right, which is about log base, the natural base log of n, right? That's the typical degree of the root, and you can easily prove a central limit theorem for this. This is just a sum of independent Bernoulli random variables. Okay. However, the maximum degree is much larger than this, and this is well known in about uniform attachment trees, that the maximum degree is log base 2 of n. Okay, so it's a constant times larger than the degree of the root. So if we choose the highest degree vertices, then if we only choose a constant number of them that doesn't depend on n, then we will miss, with high probability, we will miss the root. That's easy to see. Okay, so sorting by degrees is not gonna work. Okay, the preferential attachment model, this idea works a little bit better, but it's still far from being optimal. Okay, there, as I said, the maximum degree is of the order of square root of n, so it's a very different story. Okay, so what can we do if not sorting by degrees? Well, the idea is go by centrality. Okay, so this is a really simple method, and I will show you how it works. That chooses the most central vertices. So how do we define centrality of a tree? Well, there are various ways of doing this, and this notion is sometimes called the Jordan centrality of the tree, which simply for each vertex we can look at all these subtrees that hang off this vertex v. We can look at the size of the largest subtree. Okay. And a vertex is called central if the size of the largest subtree is as small as possible. Okay, so if a vertex is somehow in the bulk, in the middle of the tree, then all subtrees will be somehow smallish. Okay, whereas if you look at for example, if you look at a leaf here, then it has only one subtree hanging off it, and that has size n-1, so it's huge. Okay. But there's always a vertex such that the largest subtree is at most n-half. Okay. So that's our first root finding idea. Let's take the k vertices that are most central in this sense, right? So we just sort vertices according to the maximal subtree size, and we pick the k smallest of these guys. And now it's not difficult to prove, and I will show you the sketch in the next slide. That if k is about 1 over epsilon, well, it's 11 log 1 over epsilon, but the main order is 1 over epsilon. So if k is bigger than 1 over epsilon, then with probability at least 1 minus epsilon, we will hit we will hit the root. Okay, so the root will be among the most central vertices, the 1 over epsilon or 11 log 1 over epsilon most central vertices. Okay, so here's a really ugly slide about the proof. This is just a very simple sketch. So what do? We label the vertices chronologically. Okay, as we did so far. So vertex number 1 is labeled by 1, vertex number 2 is 2, and so on. And psi of I denotes this statistic that we work with. So this is the maximum subtree size of vertex I. Okay. So how can it be that the root is not among the k most central vertices? Okay. Well, this will certainly happen if there exists a late coming vertex that is more central than the root. Okay. But if a late coming vertex is not more central than the root, this can happen by two different reasons. Either the root is not very central, or this late coming vertex is very central. Okay, so either so the probability that the root is not among the most central vertices can be upper bounded by the probability that the root is not central. And by not central, I just this is the right threshold. I could put any threshold here, 1 minus epsilon n, 1 minus epsilon n. This is the one that will give us the optimal balance. So this is the probability that the root is not has a subtree size which is very large, at least 1 minus epsilon times n size. Moreover, no vertex. There exists a late coming vertex that has no subtree size which is bigger than this. Okay, that is very central. Okay, so how do we bound the first vertex? Well, you see, this is vertex number 1 and this is vertex number 2, and let's put everything in one bag that attaches to vertex 1, including what attaches to its to the vertices to attach to 1, right? So these are all the subtrees that hang off 1, and the B is all the vertices in subtrees that hang off vertex 2, right? So we can partition the vertices in two ways, and you see these two bags behave like a polyarn, a very simple polyarn, where, because when a new vertex arrives, right, then then it will attach to either A or to B, and the probability that attaches to A is just proportional to the number of vertices in A. So this is the simplest possible polyiron. Okay, and we know that the sizes of polyiron with this really simple replacement rule is uniform. Okay, so these two subtrees are uniform. So the probability that that the vertex one is has a subtree which is bigger than 1 minus n, which is that's smaller. Sorry, this psi 1 is definitely smaller than the larger of these two urns. But the larger of these two urns, well, these two urns are about uniformly distributed if we divide by n. So the probability that this is bigger than 1 minus epsilon times n is bounded by 2 epsilon. Okay, so this is how we bound the first term. And the second term is similarly a polyiron argument, because how can it happen that a late coming vertex I, which is not among the first k vertices, late coming vertex is very central? Well, if this is very central, that means that all these trees have a small size, right? Size less than 1 minus epsilon, because of, right? So and that again, these bags behave as a polyiron, so we can just use the limit theory of polyarons and conclude that this probability is smaller than k times 1 minus epsilon to the k minus 1, and then if we optimize k, then we get that if k is about 1 over epsilon log 1 over epsilon, then the probability that the root is not among the k most central vertices is going to be smaller than epsilon. Okay, so that's a really simple rule. And and this analysis is actually sharp in the sense that that up to this logarithmic factor, we cannot do better with this particular method, right? And the simple reason is that the root remains a leaf for after k steps with probability 1 over k. Okay, so so that means that after let's say 3k steps, the root is still a leaf with this probability. Okay, and that means that at that time the root is not going to be among the k most central vertices, and then it's easy to conclude that k has to be less than if bigger than 1 over epsilon. Okay, so so the question is, can we do better than 1 over epsilon for this k? Well, we can try to find the optimum rule. Okay, so what's the optimum rule? The optimum way of finding the root is the maximum likelihood. Okay, because for each vertex we can calculate what's the likelihood that that vertex is the root of the tree. Okay, so what does this mean? We can imagine for each vertex that that vertex is the root, and now we can count how many different ways the resulting tree could have been produced, right, by recursive labelings of the tree. Okay, and if we do that, then it turns out that the likelihood function is proportional to this expression. So let me explain what is this. So this TUV down arrow is the subtree of the tree rooted at u. So here we imagine that u is the root of the tree, and we look away from the root, and so this is vertex u, and this is vertex v. So we just look at this subtree size. Okay, the subtree of v when we look away from the root. Okay, so for each vertex we take the product of these subtree sizes. Okay, and this and we have to worry about automorphisms, but let me just not even explain what that term is. Okay, so the point is that this is the maximum likelihood. Okay, so we know what the optimum rule is. The problem is that this is complicated expression, so it's not very easy to analyze it. However, we can analyze it to get lower bounds. So I'm not going to go too much into the details, but with a very simple argument, we can prove that if k is smaller than something like e to the square root of log 1 over epsilon, this is much smaller than 1 over epsilon, then no method can work. Okay, so this is a lower bound that we have. Let me not go into the details. And we can also try to improve our upper bound that we got from the simple way of just finding the most central vertices by trying to analyze the maximum likelihood directly. We couldn't do that because of this annoying term that involves these automorphisms. So we just said, okay, so let's just pretend that it's not there, and let's try to minimize this function. Okay, so now instead of looking at just the subtrees that hang off a vertex, we look at for every vertex apart from this vertex u, we look at the subtree size that looks away from u, and we take the product of all those. Okay, so this is our new centrality measure. Okay, and we would like to minimize this. Okay, so this is a little bit more complicated than just looking at the sizes. And it turns out that this is better. This is strictly better than looking at Jordan centrality. What we could prove is that if k is larger than e to the log 1 over epsilon over log 1 over epsilon, then the k vertices that minimize this statistic, so the most central vertices according to this measure will contain the root with probability 1 minus epsilon. Okay, and you see, because of the presence of this log 1 over epsilon in the denominator of the exponent, this is much better than any power of epsilon. Okay, so in particular, it's much better than 1 over epsilon that we had before. Okay.
So, Gabor, would you take a question now?
Of course, yes.
So there was a question earlier by Devavrat about commenting on both these algorithms, the complexity as a function of n, the size of the network.
This is maybe I skipped the slide where yes. So here, finding the most central vertices is really easy because this function is monotone along paths. So computation is really easy. It can be done in linear time. And this other one, that's a good question. The maximum likelihood that could be much harder. But yeah.
I also had a question. Now, you started with this application of finding the first patient.
Yeah.
Now, at least in India, we have a lot of missing data. So edges may be missing. Can you do something then?
These are wonderful questions. Yes, this whole area is kind of in its infancy. So there are many exciting questions. And yeah, I would love to hear nice models. So it's sometimes, sometimes problems are immediately too hard. Sometimes they're immediately too easy. So it's interesting to find a nice model when you can kind of understand, for example, missing edges or missing data.
But from your analysis, wouldn't it be? It seems that if you just miss a few edges, since you're doing everything is based on sizes, it may not be that. You may be able to tolerate loss of a few edges. No.
Well, it's a tree, so if you lose an edge, then the graph disconnects. So yeah, I don't know how one can formulate this in the right way here. Yeah, I don't know what the missing edge means here. Maybe in other models when we don't have trees, then yes, then there should be some robustness. Here, I don't know how one can deal with that. Yeah. Yeah, though maybe even in trees there's hope because somehow edges, if you don't have too many missing edges, that maybe you can argue that the bulk of the tree remains the same. Maybe, but that's very interesting actually.
If that has one more question, you'll probably answer it. He's saying, is the conjecture that 1 by epsilon is the right answer? Is 1 by epsilon the right order?
Well, no, one over epsilon is not the best, because we can do better, right? We can do this. E to the log 1 over epsilon over log 1 over epsilon. And so I have a summary here on this slide. So there's still a big gap between the lower bound and the upper bound. I would guess that the upper bound is closer to the truth, simply because the lower bound is such a simple-minded argument. So I don't know. And what we do know is that what I mentioned earlier is that for uniform attachment, the problem, this k is strictly larger. It's much larger. It is between 1 over epsilon and 1 over epsilon fourth. We didn't really look for the optimum in this case. I would guess it's something around about 1 over epsilon, or maybe 1 over epsilon squared for preferential attachment. And the reason, let me just say one simple word about this. The reason why this is true, why preferential attachment networks are more difficult, is because if you look at what's the probability that the root is a leaf for a long time, then it's much larger. It's, instead of 1 over k, it's 1 over square root of k. The probability that after k steps, the root is still a leaf. Okay, and the reason why this is because, so this is root number 1. This is vertex number 1, vertex number 2, and now if vertex number 3 attaches to vertex number 2, that has probability 50%, then the next vertex is now twice as likely to attach to vertex number 2 as the vertex number 1, and so on. Because of preferential attachment, if something goes wrong at the beginning, then it stays wrong for a long time. Okay, so it's much easier to miss the root. Okay, and we can prove. I'm not going to go to in the details now. We can prove that that in fact one cannot possibly hope for k better than 1 over epsilon. Okay, and this upper bound is again just a simple analysis of the Jordan centrality. So the same simple centrality measure that worked for uniform attachment also works here with the verse exponent. And the analysis is very similar, again, with a Pauli iron with a slightly different replacement rule. Okay. So this is this closes the first half of the talk. The second half is related, and I actually kind of need these results for the second half. But maybe if there are questions, this could be a good moment.
So is the lower bound here for the preferential also by taking the max likelihood, and is now would you say that that's closer to the truth?
So here, okay. So what is easy to see in the preferential attachment model is that it can happen with in a preferential attachment tree of size 1 over epsilon squared. The following can happen with high probability. Well, not high. It will happen with probability at least epsilon. Is that the root is still a leaf, and vertex number 2 has about square root of n neighbors. Okay, and that are also leaves. So there's no way of distinguishing the root from these guys. Okay, and there are square root of sorry, there are 1 over epsilon of these. Okay, if n is of this size. Okay, so that's a very simple argument. We don't have to analyze the maximum likelihood. We can also write down what the maximum likelihood is. It's not too easy to analyze. Okay, so the second problem is the so-called broadcasting problem. That is the following. So here, vertices have 2 colors, either red or blue. Okay, and the root has a random color that we don't know. Okay, and now when a new vertex attaches to so when we grow this tree, when the new vertex attaches to the parent, then it will take its color with probability 1 minus q, and take the opposite color with probability q. Okay, so think about q as a small number here, even though later I will discuss the case when q is big, but think about q as something small. Okay, so in a typical case, when a new vertex attaches to an existing vertex, then it will take the same color with high probability, but with some small probability, it's a rebellious child and it changes color. Okay. And now what we observe is an unlabeled tree, so we don't see the labels 1, 2, 3, n. It's an unlabeled tree of size n, and all we see is the colors of the vertices. Okay, so we see this red and blue vertices, and we would like to guess the color of the root. Okay, so the question is, what's the optimal probability of errors? This is a classification problem, and we would like to guess what's the color of the root. Okay, we don't know what the root vertex is. What we see is this. Okay, so sorry. So this is the tree that we generate. This is the root number 1. It's blue in this case. Then root number 2, when it attaches, it takes the same color. Vertex number 3 it takes the same color. Vertex number 4, I can't find it. It's here. Vertex number 4 was attached to 2, but it was a rebellious child. It changed its color. Okay. Vertex number 5 was not rebellious. It attached to here, and so on and so on. Okay. Vertex number 6 attached to 1, and again it was rebellious. Okay, so and so on. This is how the tree is grown. But now what we observe is this tree. We don't see, of course, these labels. So I show you this tree with the colors of the vertices, and the question is, what is the color of the root? Of course, we don't know where the root is, but can we guess the color of the root? All right, and what's the smallest probability of error that we can get? This is the classification problem. There's a more difficult variant, and this is called resembles more to the classical broadcasting problem on trees, is when we only observe what happens on the leaves of the tree. Okay, so it's the same. The tree is grown exactly the same way as before, but what we observe now is this. So we only observe the unlabeled tree, and we observe the colors of the vertices. And the question is, can we guess what's the probability? What's the color of the root? And what is the smallest probability of error that we can achieve? Okay. And in the rest of the talk, I will only consider the uniform attachment model, though we also analyze the preferential attachment model, and actually the results are quite similar. Okay. So the first obvious observation is that the smallest probability of error is at least q over 2. Okay, so why is that true? Because with probability q, vertex number 1 and with probability q, vertex number 2 is a rebellious child, and they change its color. So at time 2, with probability q, what we have is a red and a blue vertex, and from then on, these two are completely undistinguishable, and anything can happen. So on this event, we make an error with probability 1/2, no matter what. Okay, so the optimal probability of error cannot be smaller than q/2. This is completely trivial. Okay. Well, what's the optimal classifier? Well, we can determine the optimal classifier because we know for each vertex we can compute the likelihood of that vertex is the root. Remember that we had this ugly big expression. So this psi sub t of u, this is the likelihood that vertex u is the root. So what we can do is that we can add these up for all blue vertices and add up the likelihoods for all red vertices and compare them. And this is the optimal classifier. Okay, but of course this is difficult to analyze. So what we will look for now are simple classifiers, and we will see if we can what we can say about them. All right. So, of course, the first idea, especially after the first half of the talk, is that we can use root finding algorithms, right? So if we can identify the root, then of course we know the color of the root. Well, we could not really do that, right? What we could do is that we could find k epsilon vertices that contains the root with high probability. So we can just look at that subtree and take the, let's say, the majority of the vertices. Okay, so take any root finding algorithm that finds k of epsilon vertices. Look at the colors. We know that with high probability the root is among them, and take the majority vote among those. Now it's very easy to analyze this, right? Because we have with probability epsilon, we missed the root. The root is not among these guys, and if all the other vertices have the same color, then of course we're gonna be correct, right? If it's not, then it's an upper bound for the probability of error. It's actually not a bad upper bound, even though it looks very crude, but it's not a bad upper bound. So what we get is that the probability of error of such a method is at most epsilon plus q times the optimum value of k epsilon. Okay? So if we plug this back to what we had, then for the uniform attachment model, we get that the probability of error is at most q to the 1 over log q. And for the preferential attachment model, we get something much worse. All right. So this is quite interesting. Of course, now it's not that surprising that these probabilities don't depend on the size of the tree anymore, right? Because we can kind of identify the root irrespective of the size of the tree. And you see in the uniform attachment case, we are quite close to the lower bound, to that silly lower bound that was here, q half. Okay, we get, if q is very small, then this 1 over log q is sorry, there I guess there should be right. Then this is very close to linear, but it's not quite. Okay, so the question is, can we do better, right? So this is simply just plugging in the root finding algorithms. And this analysis cannot be improved. That's easy to see. However, when we would like to only guess the color of the root and not finding the root, right? Well, now we don't really care about finding the root. All we want is to find the color of the root. It makes more sense not to try to zoom in and find a small subset of the vertices that contain the root, but try to find vertices that are close to the root with high probability, right? Because if we know that a vertex is very close to the root, then with high probability it will have the same color as the root. Okay, so in particular, if we choose using some method, if we choose a vertex v, and capital D is this is a random variable, of course, it depends on our method. If D is the distance in the graph distance of this vertex to the root, then it's very easy to see that the probability that the chosen color, and we just look at the color of this vertex, then you see this method will make a mistake only if there's an odd number of times when on the path between the root and this vertex v, the number of color changes is odd, right? And the probability of that is bounded by q times the expected distance. Okay, so if we could find a vertex whose expected distance is a constant from the root, then we would get a method of guessing the root that has a probability of error proportional to q, which is the best one can do. Okay, and it turns out that this is actually very easy, right? Because what we can do is simply choose the vertex, the most central vertex, according to the Jordan centrality. Right? Remember, this Jordan centrality is just the vertex that minimizes the maximum subtree size. Okay, so let's take that central vertex. then in both the uniform and the preferential attachment model, we can prove that the root is within distance log 1 over epsilon to V star, independently of n. Okay, so in other words, the distance of the uniform, the distance of the most central node from the root is bounded by an exponential random variable. Okay, and in particular, we can prove that the expected distance is bounded by is less than 5. Okay, so it's typically very close. All right. So, and the proof is again just a very simple Polyarn argument, because for a vertex, let's suppose that there's a vertex VT here. Okay, that is such that this path has length t. Okay, now you see, how can this vertex be more central than the root? Well, it must, if this is if this vertex is the centroid, is the most central vertex, then it must be that here in this subtree that looks away from the root has more than half of the vertices. Okay, but now we have this urn model where in urn number 1 we have these t minus 1 vertices, and urn number 2 we have one vertex at time t. And now the probability that this will happen is bounded by is exponentially small. It's something like 2 to the minus t. Okay, so so this is a very simple Polyarn argument, proves that the distance of the most central vertex to the root must be bounded by an exponential random variable, meaning that the probability that that this distance is bigger than c times some constant times log 1 over epsilon is less than epsilon. Okay, and if you work out the numbers, then we get that the expected distance is at most 9 halves. All right. So so what we get, and we get this for both in the uniform and preferential attachment models, that the optimal probability of error is now is linear, is between q half and q. So when q is very small, then this silly lower bound is actually very close to the optimal. Okay, so the what makes guessing the root, the color of the root, difficult is at the very beginning there's a color change that happens with probability q. Okay, and moreover, with the same method we can also prove that whenever q is smaller than 1/2, right, meaning that remember q is the probability that a newly arrived vertex takes the same color as the parent, is smaller than 1/2. So whenever it's smaller than 1/2, then we do strictly better than random guessing. Okay, I ran out of time, so I'm gonna just very quickly wrap up. Let me just mention that in the more difficult model, when only the leaf colors are observed, the same holds. The same inequalities are still true, and the reason is that we can prove that there is always a leaf very close to the centroid. Okay, so what we can do is that choose the centroid that will not be a leaf with very high probability, but with very high probability there will be a leaf which is very close to it at most constant distance, and then our arguments work. And yeah, maybe in 10 seconds, another very simple method is just counting how many red and blue vertices are there in this big tree. Okay, and it turns out that this works if q is not too large. So in the uniform attachment model, this method will break down when q is 1/4. Okay, so when the probability of a rebellious vertex is bigger than 1/4, then taking the majority doesn't work anymore. But before that, it does, meaning that the probability of error of a simple majority is going to be strictly better than 1/2, and moreover, it is linear it is linear in the in Q at the when for small values of Q. Okay. And let me finish by giving you these two references. So the first half of the talk was about this finding Adam problem. It's a 2017 paper, and this broadcasting paper is much newer. Okay, thank you.
Thank you. There are a couple of questions. I just let the participant just kind of unmute and ask the question. So,
Of course.
Sina, if you want to go ahead, and then maybe Devavrat after that.
Yeah, thank you. Hello. So thank
Yes.
you very much. And there was this variant of the model where only some of the nodes were observable, the last one
Yes.
that you discussed.
Only
So
the leaves. Yes.
yeah, I'm not quite sure if all the information regarding the hidden ones are missed or just the colors.
So what we observe is no, just the colors. So we this is what we observe. Okay, we observe the combinatorial tree with the leaves colored.
Thank you very much.
Okay, so in particular, what we can do is that we can look at we can find the centroid of this tree, right? Let's say it's this, and now look at the a closest leaf, and take the color of that, and that will work.
Right.
So my question was just I seem to recall that there was some work by Elkanan Mossel and Yuval Perez on propagating the labels from the leaf up to
Right.
the root.
Right.
So your results should be better than theirs, I assume.
No, these are not really comparable, but yes. So they call this the broadcasting problem, but they typically consider let's say the simplest model is you take a complete binary tree, and now the root has a color. It's the same kind of propagation, and then you look at what happens at the leaves. Okay, and now they try to see up to what time, so how deeply can we go such that there's still information about this information about the root value can still be guessed. What we do is that we look at the same model for these recursive trees. Okay? Instead they look at Galton-Watson trees or this complete binary tree and the trees of that kind. Our trees are recursive trees that are very different, right? In particular, in our trees, there will be always leaves close to the root, and that's what makes it easier. Okay, because in their case, of course, all the leaves, all the information is far from the root, and then there are interesting phase transitions that happen. Okay, so, but it's the same problem, just on different kinds of trees.
Thanks.
So any more questions?
Yeah, hello. Yeah, it was a nice talk. Actually, my question was, you're saying that K doesn't depend upon N, right?
Yes.
But in the proof, it appears like you are taking the asymptotic analysis of the urn-based models, right? So in
Yes.
some sense, that's the reason why it is not depending on N. Am I?
No, of course it's a lie. I'm not saying that it's yes, it is, of course. So of course it does depend on N, but it doesn't get harder with N. Okay, so
Yeah.
the problem so of course the problem becomes harder and harder and harder, right? If N is larger in both finding the root or guessing the color of the root becomes more difficult, but in both cases in the first case, the number of vertices that we have to choose can be chosen independently of N, and that will work for all N. Okay, so of course the problem becomes harder, but not much harder. Okay, so that's I should have said it like that.
Okay. Thanks.
Yeah.
Okay, so there are no more questions. Thank you, Gabor. That was a very nice talk. Thank you very much.
Thank you.
On behalf of everyone. We have now, I guess, 3-4 minutes to get coffee and do other things that we do. So we'll start in another 3-4 minutes. let's just say by 6:31 Indian Standard Time. Thank you.